In this video, I will explain to you how to solve a combustion analysis problem. So, combustion analysis. So, if you remember how a combustion reaction undergoes, you will always have like an organic compound or a fuel that will be carbon, hydrogen, and oxygen. The X, Y, and Z means that this could be any number. Then you will have your oxidant, which is the oxygen, and you will have a given amount, you will form CO2 plus water. Those will be your products, and these will be your reactants every time. So in a combustion analysis problem, what you want to find is the fuel. You will want to find the empirical formula of the fuel that reacts with the oxygen. So a few tips before we start. You will never want to begin by quantifying the oxygen, because as you can see, there's oxygen in all of the products and the react. So you never want to start by getting the oxygen factor. In other words, let's say getting this number. That is what quantifying it. So we'll say that oxygen will be always last. However, as you can see, there's only carbon in one of the products, so you can find the carbon by using the carbon dioxide. So you can start with that, or you can start with the water, which would give you the hydrogen factor. So you can start with any of them, and then you can get the value of the oxygen. So to start a combustion analysis, what you want to do is to get the grams of each of the products. So you want the grams of the CO2 and the water and then you can get the moles from it. And when you have the grams of the CO2 and the water, you can get the grams of the oxygen too, just by a subtraction that I'll show you. And when you have the moles of all of the elements, you can simply just use the empirical formula method I showed you in a previous video. Again, to obtain the fuel of the reaction. So I'm going to solve a combustion analysis problem just to show you how a combustion reaction usually undergoes. You will be able to picture it better when you see it. So let's start. So the problem says that you have 0.6943 grams of a compound containing carbon, hydrogen, and oxygen, that being our fuel. So we have a mass of 0.6943 grams of our fuel. So let's call it CXHYOZ. The X, Y, and Z are because we don't know those numbers, so we're just putting variables there. And then they tell us that the molar mass of that compound, of that fuel, is about molar mass is about 163 grams per mole. What this tells us from the beginning is that we may have to find the molecular formula. And now, in the first part of the problem, this problem is divided into 3 parts. They tell us that we have a mass of 1.471 grams of CO2. So we have the mass of the CO2 already. And 0.226 grams of water. And the question is to find the empirical formula and molecular formula of this compound. So as I said before, the first thing we want to do is to obtain the mass of each of the elements. So we want the mass of carbon, oxygen, and hydrogen. And we're going to start this time with carbon. Doesn't matter if you start with carbon or hydrogen, but oxygen is always last. So I'm going to erase all of this just to give us a little space. To picture it a little better, I'm going to write the chemical reaction we have. So, as I explained just now, a combustion analysis undergoes a reaction like this. A combustion reaction undergoes this kind of reaction. So, you produce oxygen, CO2, and water, right? And I'm going to write the mass of each just to make it a little bit easier. We have 0.6943 grams of this. Of CO2 we have 1.471 grams. And of water we have 0.226 grams. I'm used to writing the whole word. Okay. We don't have although we don't have the grams of the oxygen, so we have to obtain that later. So as you may recall, to go from grams of CO2 to grams of carbon, let me write it first. We have to use the mole diagram that I talked about before. So just a little reminder, this is the mole diagram. We have moles of CO2. We have grams of CO2. So we are here. No, that's gas, sorry. Doesn't matter really, but we are here. And we want to go here, which would be the mass of carbon. So we have to go from mass of CO2 to the moles of CO2 to the moles of carbon to the mass of carbon by itself. So that's just a reminder. I'm going to erase it because it won't fit. So the first thing we want to do is go from grams of CO2 to moles of CO2. So we know that 1 mole of CO2 would be its molar mass, which is 44 grams of CO2. Now we want to go from moles of CO2 to moles of carbon. Well, in CO2, there's only one atom of carbon. So we'll go from 1 mole of CO2 to 1 mole of carbon. We only have one CO2, and in that CO2 we only have one carbon. And finally, we want to go from moles of carbon to grams of carbon. So a mole of carbon would simply be its atomic mass because it's just an element. So 12 grams of carbon. So the grams of CO2 go with the grams of CO2, moles go with moles, moles of carbon go with moles of carbon, and we only remain with the grams of carbon. So it is right. And we get about 0.40 grams of carbon. Now we do the same for the grams of water to get the hydrogen. So 0.226 grams equal 1 mole, 18 grams. We only have one molecule of water, one mole of water. However, there are 2 hydrogens in that mole of water. In this water, there are 2. So it's 2 moles of hydrogen. And then simply 1 mole of hydrogen is its atomic mass, which is about 1. Yeah. Just go with this. And we will get about 0.025 grams of hydrogen. So let's recap. We have the grams of carbon, we have the grams of hydrogen. So now we're only missing the grams of oxygen. So you write it. So that is what we have. So if you think about it, we have the mass of the whole molecule, of the whole fuel, of the whole compound. And we also have the carbon and the hydrogen. So if we subtract, if we say the mass of the fuel minus the mass of the carbon minus the mass of the hydrogen, we will get the mass of the oxygen. So it's a very simple formula. It's mass of compound minus mass of carbon minus mass of hydrogen gives you the mass of oxygen. And what this subtraction gives us is the mass of oxygen is about 0.268 grams. So this is pretty much the most complicated part of the problem. Now you simply have to find the empirical formula by using the method I showed you before. So let's do it really quickly. So this is what we have. We simply find the moles by the mole conversion. 1 mole of carbon is its atomic mass, 12 grams. Mole of hydrogen, 3 grams of hydrogen, and 1 mole of oxygen, 16 grams of oxygen. So let's go with this, and we'll simply have the moles of all of each of them. So we get 0.033 moles of carbon, we get 0.025 moles of hydrogen, and 0.0167 moles of oxygen. So we divide by the lowest, in this case the moles of oxygen, and we say 0.033 167, hydrogen 0.025 0.0167, finally oxygen would be 0.0167 over the same, giving us 2 here, 1.5 here, and 1 here. So we'll do it like that. And we have to multiply all of this by 2 to get that 1.5 out of the way. So this is the empirical formula. And here is this part. And well, at the beginning of the problem, they told us that the molar mass of the whole compound was about 163, right, grams per mole. Now, just to get the molecular formula, we get the molar mass of this, and when we get that it is actually the empirical mass of it. It is 83.068. So when you divide this, we get that we get a coefficient of 2 here. So we have to multiply the empirical formula by 2 to get the molecular formula. So at the end, our molecular formula would be C8H6O4, and that is the compound that we have in this equation. That's it for combustion analysis.